To a mathematician, a qubit is the complex projective line or Riemann sphere. But to a physicist, this sounds like crazy talk. I absolutely love starting with this quote because it instantly highlights this fundamental, almost rebellious tension right at the heart of quantum computing. I mean, how can two totally different disciplines look at the exact same building block of the universe, the qubit, and speak two completely different languages?
Welcome to The Explainer. We're diving straight into a fascinating paper by Simon Burton and Hussein Anwar from Quantinuum called Meromorphic Quantum Computing. Basically, what we're going to do here is translate the highly abstract textbook linear algebra of quantum mechanics into a tangible geometric story using projective algebraic geometry. We'll see exactly how states become points on a sphere, and get this, how polynomials can actually fix quantum errors.
Here's our roadmap for this explainer. 1. The quantum fluff problem. 2. Enter the Riemann sphere. 3. The meromorphic decoder. 4. Fixing quantum errors. And finally, 5. Rewriting quantum mechanics.
Okay, let's dive into Section 1, the quantum fluff problem.
To really understand why we even need a new perspective, we've got to look at the friction points in the standard kinematic axioms of quantum mechanics. So the textbook treatment picks out states using unit vectors, right? But this leaves what the authors playfully call annoying fluff on the carpet in the form of a global phase. It completely fails to give us a unique canonical representative. But if we projectivize the math, which really just means making states one-dimensional subspaces, we get rid of all that fluff. We basically trade in our old, shaggy carpet for a nice, perfectly clean one. There's a catch, though. Now we have holes in the carpet. These correspond to states that are literally ad infinity. So we've gained a ton of elegance, sure, but now we have to manage these missing points.
Section 2. Enter the Riemann sphere. So let's step away from standard linear algebra for a second and physically picture our new geometric home. Imagine the Riemann sphere mapping out the extended complex plane, and alongside it, the block octahedron. In this new projective space, these points correspond directly to the eigenvalues of linear operators. Now yes, by doing this, we have absolutely forgotten the complex eigenvalues, but in exchange, we get this incredibly clean mapping, where Pauli matrices and Clifford rotations actually correspond to physical geometric rotations that fix opposite vertices or faces of these shapes. It takes something incredibly abstract and makes it beautifully visual. Moving right along to Section 3, the meromorphic decoder. All right, now that we've got our geometric space, it is time to introduce the mathematical magic that actually unlocks its power. And hey, don't let the terminology intimidate you here. A meromorphic function is really just a fractional linear transform built out of polynomials. You know, a polynomial p over a polynomial q without any roots in common. I just want you to think of this as an elegant, almost magical mathematical decoder. It's simply a formula that maps points from one place on our Riemann sphere directly to another.
But listen, this is way more than just a neat visual trick. When we apply these projective rules, we are completely translating linear algebra into projective algebraic geometry. And doing that, it actually gives us the fundamental arithmetic of quantum computing. The actual multiplication and addition of complex numbers literally come directly from the projectivization of quantum circuits. It's wild. To see this actually in action, let's talk about ZX calculus. In tensor network notation, these circuit diagrams flow from right to left. And within these networks, we have what's called a Z-type spider, often visualized as a white node. When you projectivize this specific node, it spits out the exact rules for multiplication.
And right alongside that, we have the X-type spider, usually represented as a black node. These two spiders are the ultimate building blocks of our meromorphic circuits. And here is where it gets really incredible. When you projectivize this X-spider, the resulting meromorphic function actually perfectly mirrors the familiar formula for Lorentz velocity addition in physics. It all just beautifully connects. Which brings us to Section 4. Fixing quantum errors. Let's bring all this high-level math back to reality for a second. Why does replacing linear algebra with projective geometry actually matter to us? Well, because these meromorphic functions act as the ultimate error-correcting codes. Look, quantum computers are notoriously incredibly fragile. But by finding the stationary points of these meromorphic functions, the specific places where the derivative is precisely zero, we can mathematically suppress coherent errors. This completely unlocks new ways to understand quantum stabilizer codes and a really vital process called magic state distillation, which you absolutely need for universal quantum computing.
When a quantum system is actually running, the problem of error is immense. Think of our Riemann sphere.
The perfectly prepared states get pushed around by constant noise, creating this chaotic landscape of potential coherent errors. You've got stabilizer states, what the paper calls H states and F states, all scattered around. When a system is hit by noise, it shifts away from these ideal, perfectly plotted points, completely scattering across the surface of the sphere.
But watch what happens when we apply a specific meromorphic function, specifically Klein's octahedral function, to all that chaos. It completely simplifies. The math literally acts like a geometric funnel. All those chaotic, error-prone points are mathematically snapped into a single, beautifully clean region. It distills the messy, noisy points back into perfectly clean, usable quantum states. That right there is the sheer power of meromorphic error correction in action.
And finally, Section 5, Rewriting Quantum Mechanics.
To wrap all this up, let's zoom way, way out. Because we aren't just tweaking some algorithms here, we're looking at the foundational language of physics itself. The authors leave us with this truly brilliant thought. They say, perhaps if Heisenberg had wandered a bit further down the hallway to find an algebraic geometer instead, we would now be rewriting quantum mechanics in terms of linear algebra. History dictated that quantum mechanics was built on linear algebra. But this paper shows us, without a doubt, that projective algebraic geometry and meromorphic functions work just as well. And honestly, in the case of error correction, they might work even more elegantly. They are the true algebraic bones of quantum computing.
Which brings us to our final thought. If we can completely rewrite the foundational math of quantum mechanics just by trading a shaggy linear algebra carpet for a clean geometric sphere, what other mysteries of the universe are just waiting for a simple change in perspective? Really think about that as you process this explainer. The exact tools we need to unlock the next massive technological breakthrough might already exist. We just might be using the wrong math to look for them.